Okay, part one, Bitcoin mining. So we're going to introduce mining at the high level. We're going to show the details of the process and then go into one specific detail, difficulty adjustment. So recall from the exercise we had with a transaction, this process that a transaction is going to go through. And when it comes to mining, we're going to look at this step here in more detail, which is really sandwiched in between a full node. It's a full node, then it's a miner, and it goes back to a full node. So of course, this is going to be our topic here, what we're going to look at. This is the 4 steps of the mining process. And change the slide around a little bit. Okay, so we're gonna start here in the middle at this step in the process, step number 2. So, and we're going to start here by looking at the mempool and just going over real quick what the mempool is. Every full node is going to have a mempool, and as we have these, we saw from our transaction exercise, that the network is going to have transactions going all across it. They're always being broadcast, propagated across the network, and transactions are always being received by Bitcoin full nodes. So once a node gets a new transaction, there's a whole host of items that it's going to check this transaction for. And again, it's the full nodes who are enforcing the rules of Bitcoin. And if it's a valid transaction, then the node is going to add this to its mempool. And then only if it's valid will it forward the transaction to the other nodes on the network that it's connected to. So if it's a valid transaction, add it to the mempool, and you can see that over time the mempool will gradually be getting filled up. So now we need to go back to memspace. Let's go to the, I'm not sure if we've actually seen this before as a group, but this is a mempool. This is mempool.space. And this what mempool is it's a Bitcoin full node, but it's also set up in such a way that you can go in and explore all the information they have. It's just a good user interface to look at all the data within a full node. So here you can see these are the most recent blocks that have been published to the blockchain. This is block number 837886. This is the first candidate block that is being worked on right now. You can see some transaction fees, high priority, low priority, no priority. When a new block is being created, usually the software is going to push the highest priority fees into that block. And if you have a no priority transaction, you can probably expect to get it in the blockchain within about 24 hours. And then here you can see a little bit on the difficulty adjustment. We also have a halving coming up, which only happens every 210,000 blocks. We're getting pretty close to that. That's just in a couple weeks. So let's look here. This represents the mempool. Let's see. Okay, you guys can see it. This represents the mempool, and you can see that there are currently 116,000 transactions in the mempool. So now let's compare this to the transactions of the last few blocks. 2,700, about 3,000, almost 3,000 again. So there's a lot more unconfirmed transactions waiting in the mempool than there are transactions going into the block. And again, if you have a no priority transaction, it will be about 24 hours until you can make it into a block. So I would recommend going to mempool.space and just spending some time poking around this website. It's very, very fun. Most of it might not make sense now, but it's a good first hands-on. And just the 2 key takeaways are, there's a range of transaction fees anywhere from low to high, and just a really large number of pending unconfirmed transactions. It was over 100,000 compared to how many are in the block. So one last thing to point out. Actually, I need to bring this back in. One last thing to point out is we're going to go to the last block that was mined, and I'm going to go into the transactions. So here, where are the transaction details? Okay, well, I don't know what I was trying to do with that, so I apologize, but let's look here at the transaction ID. There's a host of data within each transaction. If you remember all of our transaction data, what it's supposed to have in it, and I was trying to show that with the website. But there's also a bunch of other admin information. This transaction ID, it represents all of that data, represents the hash value of all of that data. So I want you to keep that in mind for now. And I'm going to, apologies, I'm a little bit over the place here. So I'm going to copy the hash value of that transaction. Okay, now I'm back on track here. Here is the hash value, and you can recall from our the base 58 conversation that we did. This address is using only these characters. This is a base 16. It's using this representation 0 to 9 A through F to represent these binary digits. So it's got the SHA-256, the 256 bits is represented by these 64 characters. And again, the transaction ID, it's a unique identifier for every Bitcoin transaction, and it plays an important role in some concepts that will be coming up in future videos. So now getting started on a new block, this occurs about every 10 minutes, and the full node is going to siphon a few thousand plus or minus pending transactions, usually the ones that are offering to pay the highest fees from the mempool to include in this block. And one more thing to show on this transaction. This is for this transaction, one thing you can look at on mempool is you can see where the address that the Bitcoin is going to, and also they have this little fork here that shows you what the fee is being paid. So when a new block starts, the number of transactions, and when the new block starts, the number of transactions in the mempool are going to go down a little bit. And this is a repetitive process. So it's going to gradually go back up and then back down and then so on. I think you get the point. So that's it for mempool. Transactions moving into the candidate block. So now we're going to go into the next step, which is really where all the moving pieces are going to happen. This is where we actually hash all of the block of data. And we're not going to cover the Merkle root right now. That'll be a few videos from now. But we do need to first review the SHA-256 hash function. So SHA-256, or really any hash function, it's going to take data of any size, could be any size document. It's going to break it into little parses, parse it apart one at a time. It's going to run all the data through this scrambling, iterative mixing process, and it's going to result in this 256-bit output that is unique and random. So this is 256 bits long, 256 zeros and ones represented here as hexadecimal, again, base 16. And if you're given this as a starting point, there is no way to reverse engineer or trace back this process to arrive at the original data. And further, if you're given this and you're not given the original data, there's no way that you can create your own data that you can put through this process and yield this hash value. So it's a quick recap on the hash functions. And as we saw earlier, the candidate block is going to be about this size, have this many transactions. And you can think of this data as, and literally it's just a big pile of zeros and ones. And to be to get exact, it is 16 million zeros and ones, 16 million bits, will make up about 2 megabytes. And this is what's going to pass through the SHA-256. All right, so I changed the slide up and put an example on here. And we're going to walk through this to understand this here, these leading zeros. This is the big piece of this and how the algorithm targets these. So in this example, this is a base 16 representation. The number 6 here means that these are our first 4 bits in the hash value. Because here's 6, here's the bits that it represents. So we've got a 0 here at the start. So in order to produce a value that has a hash value that has one leading 0, or let's look now at 4 leading zeros. So let's say we wanted to make this a 0 in hexadecimal, which is 4 binary 0 bits. Our chance of doing that is 1 over 16. So we have to do 16 hash attempts through the SHA-256, change a little bit of data, do a hash attempt. We got to do that on average 16 times, and one of those chances we will arrive at a hash result that has, or during one of those attempts we'll arrive at a hash result with 4 leading binary 0 bits. And so this is such a target like this is what Bitcoin miners have as their hash target. And I mean, it's currently dozens of zeros, but they're trying to hash a result, change a little bit of this data, hash, check, change again until they get a certain amount of leading zeros. So okay, moved around the slide again. We're gonna walk through this in a little bit more detail. So miners they use what's called a nonce, and there's a couple locations they have. Let's show this on the latest block. Okay, here are the details. Okay, so you can see here the nonce is where they can add characters, and this is called a Coinbase transaction. We're not going to cover it now. This is the money or the Bitcoin paid to the miner as a reward. But miners have an input onto what this text reads. So it's another way they can go in and change their variables. But they have the ability to make changes to this group of data here to alter this. So initially, though, these fields are going to be blank, and they're going to run the hash just on the transactions, the previous hash result, some admin stuff like date and time. And they're going to run that and check and see if there are enough leading zeros. And most likely there won't be, so now the nonce comes into play. So what we have now is, we're adding something to the nonce field, which means we're just changing, maybe we're just changing 1 bit, or we're adding 1 bit into this data, and we know from our hash functions that it's going to completely change this target output. And so we're going to change the data a little bit, run the algorithm again, get a new hash result, check, and then repeat. And then our path forward is just to cycle through all of the possible nonce values. And there's a lot of potential values of the nonce that miners have, and they're just going to constantly update and constantly check and continue down this path. So we're going to look again at the current mempool. We're going to go to the latest block. Okay, this is the hash of the latest block. Okay, and let's just show the hexadecimal zeros here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there's 19 hexadecimal zeros, which means there are 76 leading binary 0 bits. Quite a bit. That's the current hash rate, and we're going to come back to this when we talk the difficulty adjustment. But that is not a small amount of zeros, and the work required to get those leading zeros. This is stemming from the hash power amongst the entire network. The cumulative hash power of the miners spread worldwide. It's from miners all around the world combined that are producing the power necessary for one of them to find a block that has a sufficient amount of leading zeros in the beginning. So now this brings us back. So really, there's only one thing happening in this step, and this is very specialized hardware. Is taking in all of this block data, running it through an algorithm, changing the nonce, and repeating. That's all it's doing, changing a nonce and repeating a hash. And we'll talk this more in a future video, but they're doing it as fast as they can because all miners are in a race to find this target hash because there is a reward for doing so. So now to move on to the next step, step 4, one of two things is going to happen. So I changed the slide up here. I moved 4 over. I moved 1 down. So one of two things is going to happen. One, your miner, and you have a full node, you have specialized mining equipment, you have found the hash target. You have won the race. You found the 19 leading zeros. As soon as you have it, you're going to broadcast this out to the network, and then you're immediately going to move on to the next step. Or the other thing that can happen is someone else sends you a block with the correct hash target, and they've found the correct number of leading zeros. You receive their block, and you confirm it's valid, and then you move on to the next step. And then note that when you receive a candidate block from someone else on the network, it might have taken them 10 minutes and an enormous amount of work to find that, but they're giving you all the information, all the data, all the nonce. You only have to run SHA-256 once to verify that it's a valid candidate block. So another way to view this, all said, there's not too much complexity here. Whenever a new block occurs, every full node pulls new transactions from the mempool, creates a candidate block, and then iterates a nonce value and runs SHA-256 in the hopes of getting a hash value with a winning amount of leading zeros. And this process just repeats. So the miner process is straightforward, but also it's this process of iterative search for a hash value with certain leading zeros is actually at the overlap of several very big ideas. And we've got economics here, we've got human behavior, we've got accounting, and we're gonna dedicate separate videos to each one of these major ideas. But this process of mining is in the middle of all of them. And we're just gonna look at this for now, the difficulty adjustment, and we're just gonna look specifically at what this process looks like. So the numbers we just saw, the number of hashes that are attempted by all the miners in the network every second, make 19 leading zeros. We're currently sitting at in the range of exahash per second. We'll come back to that here in a minute, give you more insight onto that. But compare this now to when Bitcoin first started. It took millions of hash attempts per second, which is not very much. So this was back in 2009. Even a basic laptop could do this. And you can see the hash rate has grown over time. And then this is an exponential growth. So each step here, giga, tera, peta, these are 1,000 times more than the previous. And as we just saw, we're at an exahash. The network is getting close to a zetta of hash attempts per second. But despite all this changing hash power, each one of these periods, the time required for all the miners in the world combined to find this hash target with a certain number of leading zeros has very consistently stayed at an average of 10 minutes. And that's due to what's called the difficulty adjustment, which can change and does change the number of leading zeros required for a valid block. And it's the 10-minute piece of this that enables the store value function, which in turn overlaps with monetary incentives and incentives to protect the accounting or ledger network. But for now, let's just see how it works. So back to mempool again. Okay, we're going to look at the mining. And this will show us a graph here on the hash rate. Okay, so looks like it's showing up like a dark pink or a red. So this straight line here goes straight down, straight across, and here it's going straight up, straight across. This straight line here is the difficulty adjustment. And you can see it says difficulty 81.73, and there's a capital T. That T represents a ratio. I don't know why they express it that way. What the difficulty is really referring to is the number of leading zeros that are required. And you can also see that See, this is February 15th. It went up, and then February 29th or March 1st when it goes back down. So and then March 1st to March 15th is when it goes back up. So every 2 weeks you can see that the difficulty adjustment is changed. And it's every 2016 blocks, which you do the math is 14 days. So the full node, the Bitcoin software on the full node, it just does a review. It compares the actual time of the last 2016 blocks versus the time that it expected to achieve. And this is back to this piece of the dashboard. So the last 2016 blocks so far have averaged under 10 minutes. So in 5 days, when the next adjustment is coming, we're projecting to increase difficulty by 1%. And the difficulty can both be increased and decreased. The difficulty is just adjusting the number of leading zeros required. So this is the hash of the very first block that was ever mined. And long story short, just ignore these two. There were 8 leading zeros required. That's hexadecimal. So 32 bit zeros that were required. And 32 is small enough that you can crunch these numbers just using Excel. So you can see in the very first block, Bitcoin was in the mega hash per second range. So this is the latest block that we hash. We counted the 19 zeros. You also have to count 1 here, which is going to give us 19, 20, 21, 22 zeros, because this 1 represents these characters. And now let's move into so yeah, this would be 79 leading bit zeros is what we're saying. And this number over here is 2 raised to the power of 79. This number is the number of hash attempts needed to find a correct hash or a hash with 79 leading zeros. Okay, so I cheated a little bit before this video, and I backed into to some numbers. So this number here is this number just divided by 600 minutes or 600 seconds to make a 10-minute block. So this is the hash attempts required per second. This is roughly 500 exahash per second, which equates to over 300 sextillion hash attempts per block. So if we pull back in the mining dashboard, so we can see that the current difficulty is roughly 619 exahash. So we're running a little bit on average more than 78 leading zeros. So even though we just counted 79, that does happen. The network is trending more towards 78 leading zeros right now. And that takes us back to our starting point is when we compare the actual time versus target time, there's actually some nuances into how the software performs this, but essentially we're just increasing the amount of leading zeros, or we're just going to decrease the amount of leading zeros. And that's how we keep blocks at 10 minutes, spaced out every 10 minutes. And this idea of adjustment is also super common in electrical systems. So just think about like the thermostat in your house. It's going to measure the temperature, and then it's going to compare it to what you set the temperature to, and then it's going to send that difference to a controller, which goes through some action to make some adjustments. It's a very common idea. This is not something that's Bitcoin specific. And then likewise, these large strings of zeros, this idea has many applications all over the field of cryptography. It's also something that is not a Bitcoin specific concept. So the function here, this iterative cycle that Bitcoin mining performs, is very narrow and it's simple. It has all the data, checks the number of zeros, increments the nonce, and repeats. And the difficulty adjustment here, which is managed by the full node, by the Bitcoin software, is going to keep this block time to 10 minutes. which helps us overlap with the Bitcoin supply issuance and monetary properties and protection of the network and so on. And at the time of this video, so right now, and then the block that we just saw, all the miners across the globe combined are doing this process about 500 quintillion times per every second.